So let's move on to the alignment of horizontal curve. So in horizontal curve, as we know that as the vehicle travels along a curve, the curve will impart a centrifugal force at the outside of the outer wheel of the vehicle, right? As we know that this is the outer wheel and this is the inner wheel, and the vehicle is moving like this. So the centrifugal force will be imparted on the outer wheel of the vehicle. So what is an centrifugal force? You can say centrifugal force impacts on the outer force on the vehicle in a horizontal curve. This force is counteracted to a certain extent by the transverse frictional force. We know that in road, the frictional force will occur between the tire of the vehicle and the road pavement, and it will impart a frictional force which will occur in this portion. So it will counteract the centrifugal force which is occurring outside the curve. This is occurring outside the curve, and the frictional force will occur inside the curve. I mean, this is the tire of the vehicle, so it will somehow it is counteracted by the frictional transverse frictional force. So as we can see in this figure as well, we can see it, right? So this is a vehicle, right? This is a vehicle. As I'm the I think the diagram is not that clear, but and this is this is the centrifugal force P, and this is the tire of the vehicle. I've given it right at, and obviously we know the pavement will impart a reaction to the tire, and let it be this point as B, and the reaction is RB, this point as A, and the reaction is RA, and B by 2 is the distance of this wheel to the center of the vehicle, and B by 2 is the distance of this wheel to the center of the vehicle, and H is the height of the tire above the height of the pavement surface, height of the center of gravity of the vehicle to the pavement surface, and this is known as the H. And if the centrifugal force is acting on this direction, so we can see that this frictional force will be acting opposite to the centrifugal force, and it will act on both the tires, right? Like this. Okay, I'll show it in red orange portion. The frictional force will be acting like this, and the centrifugal force will be acting like this. So I think it's clear about it. And the what is frictional force? What will be the frictional force? Frictional force is mu into R. That means by mu means the coefficient of friction, and Ra is the reaction at the wheel A. So it is clear. Okay, next we know this. I think we know that the centrifugal acceleration is b square by r. It's been read in almost r plus 2, and P equals to yum A. So what will be it? Yum means W by G, we know it, and V square by R. So I'm writing like this, and if I'm expressing my W in weight of the vehicle in kg, then the centrifugal force will be also expressed in kg, and R is expressed in meter. I'm writing about it. And what will be the centrifugal ratio? Centrifugal ratio means P by W. That would be WV square by no, WV not RG. V square by RG. It will be V square by RG, right? So let's move on to the following effects. What will be the effects that the centrifugal force should occur? Will impart on the vehicle. What will be the effect that centrifugal force will impart on the vehicle? So the first effect is tendency to overturn. Obviously, we know that the vehicle in moving in the horizontal curve, the outer wheel is acting as a force like this, and the after if the outer wheel force is acted like this, then the vehicle will be, you know, this like vehicle will overturn about this outer wheel. You can imagine, right? The vehicle will be like this kind of, the vehicle will overturn. This is the portion, this is the road pavement, then the vehicle will overturn like this. So this is an tendency to overturn. An outer wheel of the vehicle will be about centrifugal force overturn of and what which will prevent this. This is overturned by this P force, right? Overturn at this force, the vehicle is overturning like this, as I'm showing in the arrow, and the centrifugal forces is acting like this, and the centrifugal force will impart an moment like this, P into H, because the center to the road pavement is H. So the overturning moment is P into H. And what which force will oppose this overturning moment? like the vehicle is overturning by this p force, and the weight will be directed towards downward, and the weight component will act as an restoring moment against this p into h. We can visualize it, right? So p into h is or overturning moment, and it will be resisted by this weight into, we previously discussed about the center of gravity of the vehicle to the wheel is, the distance between them is b by 2. So it's b by 2. So p by w equals to b by 2h, obviously we know. And for if this is in equilibrium, that means p by w, we know that b square by rg, right? We explained it in previous time, and equals to b by 2h. If this would be equal, then the vehicle will overturn. At equilibrium too, the vehicle can overturn. But for the vehicle to be in safe state, the b by 2h should be greater than v square by rg. Why? Because this is the vehicle property. V is the vehicle property, H is the vehicle property, but the V and this RG, they are like the radius of the curve and the velocity of the vehicle. Velocity of the vehicle is not a vehicle property, it is the driver property, right? So B by 2 as vehicle property should be more than the curve, more than the things that the curve can impact, right? The velocity, if the velocity is high, then the curve will impact more, and if the radius of the curvature is very high, then there will be like a sharp turn, and that will cause a bit overturning phenomena. So this vehicle property should always be more than the property that the curve will impact. And the next one is to tendency to skid laterally outward. What do you mean by the skid laterally outward? As we know that this is the curve, the vehicle moving on the curve can slip away like this, because the centrifugal force should always drag this vehicle to move away from its position. And if, well, the moment is balanced, but the frictional force is not sufficient to balance the centrifugal force, then the vehicle can skid outward. So that's we have been written at. So total frictional force is given as F into Ra plus Rb. We know that Fa plus Fb will be the total frictional force. And at if this is Ra, this is Rb, A and B, and the weight is like this. So on using the equilibrium condition at y direction, y would be Ra plus Rb. We know that. So F into W is written as like this. And we know the p yaf is the frictional force. So the frictional force should be at critical case, the frictional force should be equals to the centrifugal force. So p by p equals to yaf w, and p by w equals to yaf. So p by w equals to b square by rg equals to yaf, and yaf should be greater than b square rg, so that the equilibrium condition can occur. If this is the condition, then obviously the vehicle can skid, so there is no coming back. So let's move on to the super elevation. We already discussed about how the vehicle would be affected by the centrifugal force in the curve, and it is a very dangerous thing to be there. So to avoid this problem, we introduce the super elevation. What do you mean by super elevation? Simple, it is the raising of the outraise of the pavement with respect to the inner raise at the horizontal curve. So if we cut this in x section, then we'd be seeing like the curve is like this, the vehicle cross section, it would be like this. So the vehicle would move like this. So what would this kind of shape would do? This kind of shape will prevent the vehicular centrifugal force. The centrifugal force will be acting in horizontal direction, and the centrifugal force would be resisted by a lot of components. If we provide like this, then there will be inclination, and w will be there, and its component will be there, and the p will be also divided into two components, so that's why the p force, centrifugal force effects, will also be divided. That's why there will be a bit stabilized condition if we provide the super elevation. So I have written it like raising of outraise of the pavement with respect to the inner raise at the horizontal curve to counteract the centrifugal force throughout. The super elevation is provided throughout the length of the curve. In straight portion, the camber is provided, and we eliminate those camber into forming a super elevation. At last we'll be explaining how to provide the super elevation as well. So the tendency of the vehicle would be like this, and it will move like this, and this is the outer edge, this is the inner edge. Outer edge is raised, inner edge is depressed, and the centrifugal force will be acting outwards, centripetal force will be acting inward. The figure is showing like that. And what is super elevation? Super elevation is basically this tan theta. It is a kind of slope. It is a slope, not kind of slope, it is a slope. And tan theta will be E by B. What is E? E is the height of the outrace, B is the width of the pavement. Obviously, we know it. So let's move on to this figure. And I think this figure is pretty much very clear, because this is the vehicle, and I'll be using some, and this is the, what we say, this is the wheel of the vehicle. And let's move on to these forces. So this is the P force, that is the centrifugal force, and this is the W force, that is the weight of the vehicle. It's not shown clearly. And this is the frictional force, this is the frictional force, this is the normal reaction, this is the normal reaction, RA. And this is the angle theta. So on resolving, you get it like, this will also be theta, and this angle would be theta. We know about it, right? We have read much about this kind of resolution. And let's move on forward. So tan theta equals to E by B. So theta is very very small, and we can assume at E equals to E by B. Theta is very very small, so it can be turned like theta equals to E by B, and theta is basically the super elevation. Super elevation is basically an inclination, that is theta. So theta would be very small, the value of super elevation is very small, and at a very small theta value, the tan theta would be nearly about theta, like tan 5 is nearly about 5. So you can use the calculator as well. So tan 5 would be, no, no, no. Tan 5 is very higher value, right? So tan 0.002, and it would be like, you can understand it that if the theta is very small, then the tan theta value would be very near about theta. So considering the positive direction in horizontal axis, then summation of fx equals to 0, and that means p cos theta equals to, okay, let's look at this figure. So in horizontal direction means the direction along this, along the roadway. So in this direction, we are considering this direction as positive. Oh, no, no, no. We are considering at this direction as positive. So what will be its equation? Let's write the equation. All right. So let's write the equation. That will be uh, W sine theta equals to P cos theta, and in this direction it is given as dot plus E of W. You would be understanding this, right? Because W sine theta plus, in this direction, in where this is the vehicle, so I mean F and FB would be in direction, and W sine theta would be in direction, P cos theta is in this direction. So we are written as like this. We understand it. So what will be RA plus RB? We cannot write RA plus RB as W, because RA is in this point, RB is in this point, and this is the portion where we are going to resolve. W is here, and this angle is W, so W cos theta will be here, and P is here, P theta will be here. So what would be this? P sine theta. So RA plus RB resolving in vertical direction would be W cos theta plus P sine theta. So RA plus RB is written as, look here, W cos theta plus P sine theta, and it will be multiplied by F. You can see it here. This is the bracket portion. Okay. So we have got like this, and we bring this Fp sin theta in opposite direction. P cos theta minus Fp sin theta equals to W cos theta, AW sin theta plus FW cos theta. So we divide it by W cos theta, and P by W minus F P by W tan theta equals to tan theta plus F. We know that tan theta equals to E, right? And on solving it, we get at P by W equals to F plus tan theta divided by 1 minus of tan theta, and P by W equals to B by GR square RG, and tan theta plus F equals by 1 minus F tan theta equals to B square by RG. For design purpose, for design, in general designing, we consider super elevation as maximum super elevation value will be 0.07, that is 7% super elevation is provided, gradient is provided, right? And an F value, coefficient of friction, is provided at 0.15. Normally we provide 0.15 maximum coefficient of friction, we provide it as 0.15. So for design purpose, we take the coefficient of lateral, this is the lateral friction, not a longitudinal friction. Longitudinal friction means along the direction of the road. Along this direction is called the longitudinal friction, and along this direction is called the lateral friction. Along the cross section of the road is called the lateral friction, right? So uh, transverse slope due to the E equals to 7%. So on 1 minus F tan theta, well, keep this theta at 0.07 and F at 0.15, and we solve it, then the value would be nearly 0. So 1 minus 0 equals to 1 for the design purpose. So tan theta on keeping this 1 value, if we keep here 1, then it will be tan theta plus F equals to B square by RG. So it's written like this, and tan theta equals to E of B square by RG is the super elevation, B is the design speed, and G equals to 9.81 meter per second square, R is the radius of curvature. If we generally keep the V in the form of kilometer per hour, okay, so E plus F equals to B square by RG, right? So B, if we convert this small b, that is in meter per second, then it will be 0.278 capital B. If B is in kilometer per second, it will be like this. Well, if we say 15 meter per second, then it will be 0.278 into capital B, and capital B would be around 50 kilometer per hour. Well, I can say it. Yeah, 53.9, that is around 54 kilometer per hour will be the capital B. So capital B is in kmph, kilometer per hour. So on solving this, we'll get as B square by 127R, and this is the very important formula, you need to memorize it for the numerical. And the maximum value of super elevation is 7%. But if there is a snow condition, in snow condition we can keep the super elevation up to 10% as well. Minimum value of super elevation is the camber of the road. We know about it, camber of the road, that is n%. And when F equals to 0, that is the equilibrium one. F equals to 0 means that the internal pressure on this both tire will be 0, because there is no friction, then there will be no pressure. So this pressure on this tire is 0. That is coefficient of friction is almost, the road is very smooth. So yeah, when F equals to 0, then whole the centrifugal force is resisted by this super elevation. Okay. And if for the mixed traffic condition, we consider as B as 0.75% B, and our final output will be B square by 225R, and this is the also the very important formula that you should remember. And well, let's move on to the next topic, that is method of providing the super elevation. Generally there are two methods of providing the super elevation. One is elimination of the crown of the camber section. This is the camber section, and we eliminate this crown. We gradually eliminate this crown. And another one is the rotation of the pavement to attain the full super elevation. We rotate this pavement in such a way that the full super elevation is attained. Okay. So the first method, well, I'm explaining about this one, elimination of the crown of the camber section. So in the first method, the outer half of the camber is rotated over the crown so that the outer surface fall on the same plane as the inner half. That means this is the outer half, this is the outer curve, this is the inner portion of the curve, right? So this is an in a straight line. In a straight line, we provide this like a camber, and after that we start to fill up this outer half. We started filling up this outer half, and after certain time the outer half will be like this, and after certain distance the outer half will be like this, and after certain distance the outer half will be like this, and this will be in same plane. Well, this is not clearly shown in the figure, but This would be in same plane. The inner half and the outer half will be in same plane, and after this we attain a full super elevation. So like this we will be providing the full super elevation. So we have obviously our theory portion is also clear. The outer half of the camber is rotated above the crown so that the outer surface fall on the same plane. And the next portion is we change this crown gradually so that we can obtain the full super elevation. So first the crown is in this level, and after that we started filling up this portion, and we we bring the crown to this portion, and after that we bring the crown to this portion, and this is the final super elevation that we gain in the curve. We provide the super elevation along the curve, right? So in this state, this is the straight portion and this is the curve. Then we started providing the super elevation along this portion, and gradually the super elevation will be provided in full state in the curve, and it will continue till the end of the curve, and after that the super elevation is decreased, and we finally in a straight portion we obtain the camber portion. So basically we transit from camber to super elevation between the straight line and the curve at a certain distance. So, and in the second method, crown is progressively shifted outward. Generally, not this is generally not adapted because the crown shifting will cause the vehicle to very discomfort will be there in the vehicle. So the next method is the rotation of the pavement about the center line. About the center line, we rotate the pavement. Like in first case, we rotate the pavement about the center line. So this is the pavement. We rotate this about center line. That means we cut this portion and we fill up in this portion. So it is a very economical method of providing the super elevation, and our super elevation is attended like this wise. This is the super elevation. Okay. So under this portion, the surface of the road is rubber rotated. In this portion, the central line, the camber central line will be this, and this central line would not be changed till we provide the super elevation like this. So the central line will remain constant throughout providing the super elevation. So this is a very good method. So level of the central line is kept constant. Generally, this method is applied on the hilly region. And the next one is the rotation about the inner is. What do you mean by rotation about the inner is? This is the central line of the pavement, right? So we rotate this pavement about like this. That means we started filling up this portion, and this is the super elevation that we obtained. Okay. And in this portion, look, at first the central line was here, and after and gradually I provide the super elevation like this, like this, like this. So central line is changed. So the central line is changed, then there will be discomfort or something like that. The central line will be gradually increasing so that some problem might occur, but well, it is also a very good way of providing the super elevation. And another one is the rotation about the outrage rotation means this is the pavement. We rotate this about the outer edge. That means we cut this portion, all this portion is cut down, and this is the super elevation we get like this is the super elevation we get. So this portion is generally not adapted because we need to cut the road, and there will be a depressed formation in the road. So this portion is generally not adapted. We can obviously uh we are going to start today the numerical of the super elevation. And according to our question, the first question is the radius of the circular curve is 140 meter. So the radius equals to 140 meter. The design speed is 60 kilometer per hour. Design speed is given as like this, and the design coefficient of lateral friction, that is F value, is given as 0.15. Calculate the super elevation required if full lateral friction is assumed to develop. So full lateral friction means F is fully assumed to be developed. That means F is equals to 0.15. We know that from the formula E plus F equals to B square by 127 R that we have derived in the early class. And we have to find the super elevation, that is E equals to B square is given as 60 square 127 into 140 minus 0.15. So the answer will be 0.052. Similarly, another question is calculate the coefficient of the friction. Calculate the coefficient of the friction is if no super elevation is provided. That means E equals to 0. So we have given as E plus F equals to 60 square divided by 127 R. So we have to calculate the value of F. F equals to 60 square divided by 127 r, and if no super elevation is provided means equals to 0. So the final value will be 0.202. Similarly, the third question is calculate the equilibrium super elevation if the pressure on the inner and outer wheel should be equal. So the pressure on the inner wheel and outer wheel equals to 0 means the vehicle, we know that this is the vehicle. The pressure is 0 means there is no frictional force. That is F equals to 0. So we have to find E equals to B square by 127 R, and the value will be same 0.202. So let's move on to the next question. The next question is the design speed of a highway is 80 km per hour. There is a horizontal curve of radius. So we are given as design speed as 80 km per hour. And there is a horizontal curve of radius 100 meter is the radius of the horizontal curve. On a certain locality, calculate the super elevation needed to maintain this speed. If maximum elevation of elevation is given as maximum elevation is 1 by 15 is the maximum super elevation that we can keep on the curve is not to be exceeded. Calculate the maximum allowable speed on this horizontal curve. So we have to calculate what is the maximum allowable speed, right? So first in this type of question we have to calculate first, assuming as the coefficient of lateral friction of the road is 0. We have to first assume that the coefficient of lateral friction equals to 0. This is the design step. Okay, so first we calculate E equals to B square by 127 R. So we know that B equals to 80 square divided by 127 into R means 100. So first we calculate the value of super elevation without considering the coefficient of lateral friction. So it will be 0.5, but we know that super elevation cannot be more than, question is given as cannot be more than 1 by 15. So what is 1 by 15? 1 by 15 is near about 0.067. So our super elevation equals to 0.5, which is greater than 0.067. But our you can say our maximum super elevation is up to this mark only. But the super elevation that is required for the curve is 0.5, because we are only considering about the super elevation. So we know that the super elevation 0.5 is required, but our 5 is required, but maximum we can provide up to only 0.067. So to restrain, to restrict, to counterbalance the centrifugal force, we need the coefficient of lateral friction, right? You can understand it well, because our super elevation is only 0.067. So we need coefficient of lateral friction to counteract the centrifugal force. Now we assume that the coefficient of lateral friction is also there. So 0.067 is the super elevation. We need to find the calculate the value of F and B square by 127 R. So we calculate the F from this and we get 0.434. We know that the maximum value of coefficient of lateral friction is about 0.15. So the 0.45434 is greater than 0.15. So we cannot provide the value of F 0.434 as well, because our maximum allowable is 0.15. So we get to know that for this design speed, that is 80 kilometer per hour, our super elevation provision, maximum super elevation provision and the maximum coefficient of lateral friction will not be sufficient. So we have to decrease this design speed. So for this now we have to provide, that is the maximum value. We need to provide the maximum value because this is the allowable value. We cannot provide more than this. So let's move on to the third step, that is we need to calculate the design speed, because the design speed for 80 is not good, because if we design the road with 80 kilometer per hour, then our maximum super elevation and maximum coefficient of lateral friction will not be able to restrain the centrifugal force. So that's why, so maximum comfortable speed will be E plus F. E as given at 0.065 plus F equals to 0.15 equals to B square by 127 R. So our answer will be B equals to 52.50 kilometer per hour. So this is the maximum allowable speed. So we can apply a factor of safety as, like we can apply this a bit lower so that we can be in a safe side. So B equals to 50 kilometer per hour is the final answer. What we are given, calculate the maximum allowable speed. So maximum allowable speed will be 50 kilometer per hour. Like that we can solve this problem. So the next problem is the design speed of the highway is 75 kilometer per hour. There is a horizontal curve of radius we are given as 190 meter. Calculate the super elevation needed to maintain this speed for the mixed traffic. So we know that for mixed traffic, E plus F equals to no. For mixed traffic, we don't consider F. Okay, we only consider the value of E. So that is B square by 227 R. Because in mixed traffic, we don't consider that the lateral friction will be there. So we only consider the super elevation as there. This is the step for designing. Okay. So first we have to same as the previous one, maximum super elevation 0. More than 0.07 is not provided. We have to remember this as well. 7% is the maximum super elevation and the coefficient of friction 0.15. So let's do as a first step as we have done in the previous one. So E equals to, this is the mixed traffic. So we should use the value, we should use this formula. Okay. And on solving this, we will be getting b square 75 square divided by 227 into r is given as 190. So the value will be 0.13. So in the second step, obviously this is greater than 0.07. So our maximum super elevation is 0.07. I hope you have understood it as well. And for the second step, E plus F, we need to consider the F because obviously the super elevation exceeds the value of maximum super elevation. So super elevation will solely be not be sufficient to counterbalance the centrifugal force. So we need to have the coefficient of friction. So for this we design it like this. Okay, in this case we should design it as 127 R. All right. And right now it will be E is given at 0.07 plus F equals to 75 square divided by 127 into R is given as 190. So the answer of F will be 0.16, which is greater than 0.15. So we provide the maximum value of coefficient of friction as F equals to 0.15. All right. So this is also not sufficient because the value of F also exceeds the maximum allowable value, and the value of E also exceeds the maximum allowable E. So we need to decrease the design speed. So for decreasing the design speed, we consider 0.07 plus 0.05 equals to B square by 127 into R will be 190, and we need to calculate the value of V, and the value of V will be 72.86 kilometer per hour. So our design speed was 75, and for this design speed neither the super elevation value and the coefficient of lateral friction were able to counterbalance the centrifugal force. So we decrease the design speed. That is, now the maximum design speed will be 72.86 kilometer per hour. Like that we can calculate this value, and our numerical is completed right here. In the next video we'll be explaining about the extra widening which will be provided in the curve.